All right, so let's take a look at the homework. I gave you two code examples, one for signals and one for shared memory. And then we were supposed to, so here's the two code examples. So we were writing a program that uses signals and shared memory to have two child processes. So under the, instead of the parent. So a parent would spawn off two children and then they would go off and do their things. Work as a team to count to 10. The children should alternate between the numbers and let the other child know when they have finished with the current value. So the children need to know about each other. So this is something we were talking about last time, where if the parent creates two children, the parent knows the process ID of both children, but the children don't know how to talk to each other. Well, we're asking these two children to work together to count to 10. Who cares what job they're having to do? But in any case, they're being forced to communicate with each other to synchronize the whose job it is. So child 1 says 1, child 2 says 2, child 3 says child 1 says 3, so on and so forth. They keep just bouncing back and forth. All right, so we're going to look at doing this today, and we're going to solve a couple different problems. So one problem is how do we get the two children to know about each other's process IDs so that they can potentially communicate with each other through signals. So we're going to write that part first. So our initial goal is let the children know about each other. Okay. And once we have that ability, then we can start thinking, okay, well, how might we use that ability? So let's go in here. We'll do this with our shared memory example. All right, and the current thing I have set up here for our shared memory is we create our segment ID, and this is what we were dealing with last time, where we have a single global segment ID, which is just an integer. So when we create multiple children, that segment ID each child will get a copy of that. And the issue we were running into last time, and I explained it in a Slack message as well, also explained it right here, is this IPC private thing is kind of like a special flag. It is a shared memory key, but what it does is it triggers the operating system to generate a unique key for shared memory without us having to share a string or something like that. Well, what that means is if I call shared memory get using IPC private 3 separate times, I'm going to get 3 separate segment IDs. So we call it once, get the int for that segment ID, which should be something like a random integer. Then as we start creating the child processes, they all use that same segment ID to attach to the shared memory. All right. So we'll generate that once. The parent will then create the first child. We'll ask a question. If I'm the child, I'll go ahead and announce that I'm the first child. I'll also spit out what my process ID is that I'm going to attach to the shared memory. And I'm going to go ahead and put in that shared memory my process ID. All right. And then as of right now, we're just detaching from the shared memory, and that first child is going to sleep. All right. Second child, well, else if we're the parent, create a second child. If I'm the child, I'm sleeping for 1 second because now we're going to be talking about the solution to this problem today, but we're going to go ahead and sleep for a second while we give our brother a chance to write their process ID to the shared memory. Then we'll go ahead and we'll announce that, hey, I'm the second child. I'll attach to that same shared memory using the segment ID that we created before any of the children were created. And then this is where I had the bug before, since I copied from above. I was also going ahead and overwriting the shared memory with the other child's process ID. It's not incorrect. We're just not solving a overly helpful problem. We probably want to go ahead and get the brother's process ID first before we start making a change to shared memory. Then, depending on how you want to do this, because the goal here is now, so now this guy here has his brother's process ID. In fact, I'm going to go ahead and I'm going to say int brother PID is equal to the value stored in our shared memory. All right, so now the second child has their brother's process ID stored. Then they'll go ahead and print it out, proving that I know my brother's process ID. And then they'll go ahead and overwrite that place in shared memory with their own process ID. Okay. So again, we can kind of think about the speed of this, and we're kind of having to time it. So that's what we're going to try to fix today when we talk about semaphores. But in fact, I'll go ahead and not detach from our shared memory here yet up on the first child. And let's go ahead and have the first child wait just a couple of seconds. We probably can wait less than that, but a couple of seconds will be plenty. So now they're going to go ahead and read from shared memory, getting their brother's process ID. And then spitting that out. Maybe we'll say second child here. And then why don't we have the children also advertise their process IDs. The second child sleep. First child sleep. And they'll spit some stuff out to the screen. So first child says that their process ID is 3330. Then I'm also printing out what their process ID is. Second, and then they write their process ID to shared memory and wait. The second child, whose process ID 3331, reads in from shared memory the brother's process ID, which is 3330. So now the second child knows about the first child. And the first child then wakes back up and he reads from shared memory, that same shared memory area. Notice that he had only connected to the shared memory once. So now they are truly working with the exact same memory space. And they don't have to reattach to get the updated value. So now the first child gets the second child's process ID, which is 3331. Okay, so at the end of this, both children know about each other. Let me go ahead and just dump that line right now so it's not in the way. All right. So we can say now the children know about each other. I'm going to go ahead and put the same comment over on the other side. I probably could say it before the sleep 10, but all right, so the children know about each other. So how can we then use that ability now that they know about each other? Well, we're going to do this using, well, let me stop here. Any questions about what we just did?
What does SHMDT do?
That detaches from shared memory. Like when you're done using it.
Do you have to do that, or is that just sort of best practices?
I would say best practices. I'm sure once the process dies, it'll detach from all shared memory.
Okay.
I don't know why I'm sleeping twice here, but whatever. Okay, so now the children know about each other. So now we need to create this cadence of the two children going back and forth. To do their count. Now, what we can do is we can have a starter count variable. Actually, you know what you could do? You could have, well, let's do this a couple different ways. One way is we could create a starter count variable. And we'll start that off at 0. So when both children are born, they'll have a count of 0. And now we need to synchronize this in some way. We could also do our counter inside of another shared memory. That actually might make better sense. We could pull it off this way, but the shared memory. Let's do it this way first. This will be kind of a fun synchronization. All right, so both children are going to get a variable called count and start it off at 0. Let's go ahead and say, since the parent isn't involved in the counting, we won't give it to the parent. So if we're the child, we're going to go ahead and create a counter that's set it equal to 0. If we're the second child, we'll give ourselves a counter and set it equal to 0. These are two separate count variables. Each child has their own local copy of count. Okay, so now the two children know about each other. We've just bounced back here. So now that we have the brother's process ID and the first child, the two children know about each other. So we're going to go ahead and start our cadence here. We're going to say while count is less than or equal to 10, we want to do some stuff. All right. So what we're going to do is we are going to actually let me. Oh, I want to use raise and kill both of them together. Let's go ahead and bring our signal stuff in. So before I actually do my counting, let's merge our signal stuff in here. So what I will do here, let me just grab some signal code real quick. So we'll give ourselves a handler for our signals. This handle signal. And we'll start off with just caught signal like this, just to show that it's working initially. And instead of printing out the signal that they caught, I'm going to print out get PID. So whoever received the signal can prove where, who they are. Okay, then we're going to go ahead and register with that signal. And we'll only have the children register. So if we're the first child, we'll go ahead and register it. I'm going to register with SIG user 1. And the name of my function is called handle signal. All right, so first child will register with that. Second child will also register with that. All right, so let's go ahead and prove that both the children are doing this correctly. So after we say first child, we'll go ahead and say raise SIG user 1. And for the second child, we'll go ahead and raise SIG user 1. I didn't, I did have signal already in there. All right, so first child, now they caught signal 3390. Second child caught signal 3391. So the reminder here for this is that with signals, we have two separate functions. When we use raise, that is a process sending its sending a signal to itself, as opposed to kill. So in this case here, the first child knows about their brother's ID, which is brother PID. We can go ahead and say kill brother PID SIG user 1. Similarly down here, after we know our brother's process ID, we can send to brother PID SIG user 1. All right, so first child is born 6501. They raise a signal to themselves 6501. Second child is born 6502. They raise a signal to themselves 6502. Second child says, I know my brother's PID 6501. Then they send the kill signal. They said SIG user 1 at their brother's process ID using kill instead of raise. The brother catches that signal, proving they're 6501. We're currently in 6502 saying, I know who my brother is, and I'm going to send him a signal. So there's the brother catching that signal saying, hey, I'm 6501. I just caught a signal. And we saw that it's 6502 who actually sent the signal. Then the first child, go ahead.
Would you say that the kill command is very poorly named?
Yes.
Okay.
And the real question is why is it named that? it's named after a system call. So if you're using the Unix operating system, there is a command called kill. And the kill command allows you to send, the default is sig kill to a process ID. So when they brought that into the C library, they're like, oh, well, what's the command to kill to send something to a process ID? Well, it's the kill command. So it's only strange if you don't know about the call that is in the if you don't know about the command of the Unix prompt. Otherwise, what would make a better sense, maybe better sense for a function name would be like send message or something like that. But yeah, it is poorly named. So second child says, hey, I know who my brother is. They go ahead and send the signal to their brother. So now they're communicating with each other. All right, so now we've proven, still having to play the timing game, we've proven that the children know about each other now, and they can send messages using the kill command. They're not sending a message, they're raising a signal at their brother. So they're waving their hand, telling their brother, maybe it's your turn. Okay. So now, and what I'm going to do is, since we're going to do our counting inside of the signal, I am actually going to make our counter global. All right, so all the process IDs get this counter that started off at 0. So the parent and both children, we're actually only going to count with the parent. All right, so when a child gets the count, they're going to go ahead and say, maybe count %D, and then maybe they'll put their process ID after that. So they're going to go ahead and display the current count along with their process ID. Then they're going to say, well, at the very least, they're going to tell their brother that they need to send a message it's their turn, because we're going to be going back and forth here. So we need to have that variable for the brother's process ID also global. We'll start off at -1. So now both children are setting their own copy of that brother PID, because when the new children were born, they get a copy of all the local variables. So when they talk about brother PID inside here, kill brother PID sig user 1, they're going to get a they're going to be using the process ID of their actual brother. All right, so let's just see this guy happen, just so we can see that the signal handler for one child can call the signal handler of the other child by sending a signal. So I'm going to remove our raise things. The thing there is just remember that raise raises a signal for the current process ID, while kill sends a signal to the other. All right. So first child sends their kill to the brother, initially raising that. Let's say, so child 2 is going to start the count. So once we get down here, both child 1 and child 2 know about each other. So then we'll go ahead and we will raise the signal to our brother, send it using the kill command. The brother will receive that here. And right now they're just going to spit out a 0 because we're not changing count yet. And then they'll tell their brother to say the count. So we should get 2 counts or 0 from 2 different children. All right, so there's our count 0 from our 2 different children. All right, now that we have our children talking through signals and shared memory for sharing the process ID, we can now go ahead and have the children try to synchronize a count. But keep in mind that each child has a separate count variable. They're not sharing that count. So the first child should go ahead and print out a 0 like they're doing now. And then they might say count plus plus. They might say count plus plus, but the next number that they are going to count is actually going to be a 2. So it's going to be 0, then a 1, then a 2, then a 3, back and forth, back and forth. So this guy actually wants to do plus equals 2. All right, so the first time a handler does this, it's going to be plus equals 2 off of the base value of count. All right, and how long are they going to keep doing this? They're going to do this while count is less than or equal to 10. Now what we'll do, so the first person who's going to start counting is actually child 2, right? Because it's child 1 that starts passing, that starts the count off. Child 1 yells at child 2, says, okay, you go ahead and start. Child 2 will count the 0, which means that child 1 is actually going to be starting their count off at 1. This is how we're going to offset it. So child 1 is going to start their count off at 1. So child 2 says count is 0, then they up their count to 2. Contact child 1. Child 1 then says my count is 1, they'll change it to 3. Contact child 2, back and forth, back and forth, back and forth until our count is equal to 0 or equal to 10 for both of them, greater than or equal, as long as it's less than or equal to 10. All right. And then what we can go ahead and do is once we get out of this, we can just do an exit 0. Both children will end up dying at that point. All right, but now we don't want our children to die before that. I'm going to actually move the shared memory detach up before we start the process rolling with our kill. So what we're going to do is just do a while 1. Have this child wait for signals. And we're going to do the same thing with the other child. So I can go ahead and take this this stuff out now. All right, so both children go ahead and share the process IDs and then just sit there and spin while they bounce back and forth with each other, the signals. And I go ahead and have both of them detached from the shared memory, since right now we're only using the shared memory for sharing the process IDs. Okay, so we're effectively in an infinite loop in the main of both children, just allowing the inter-process communication between the two signal handlers to go back and forth. Okay, now what's going to be interesting here is we have this inside of this loop, like we're going to do something 10 times. This is our signal handler. So this guy's going to go and do something a bunch of times. And what are we doing inside here? We're calling another signal handler. So these signal handlers are actually getting called over and over again, and each one's going to have its own loop in there. We probably don't want to have each one do a loop. We want to have each one do its thing and then kind of relinquish control back to the operating system. So rather than put this stuff inside of a loop, I'm going to move it out here. We're just going to ask the question. When we get into the signal handler, if count is greater than 10, go ahead and die. All right, so we're going to do that at the very beginning. So when somebody finally calls upon me, if my count is greater than 10 and it's no longer, there's no reason to keep counting, I'll go ahead and die. Otherwise, I'll go ahead and display the current count, increment the count by 2, let my brother know it's their turn. The brother will then check their current count variable, say, oh, is the count greater than 10? If it's not yet, I'll do my next count, and then I'll increment by 2, and I'll let my brother know. But here's the catch right here. Before we die, we're going to go ahead and have to raise one more signal to our brother. So the idea here is that I need to do it in both places. The idea here is before I actually die off, I don't want to leave my brother sitting there in limbo. So I'm going to send one last command. Hey, I'm not going to count this time around, but just in case you're still alive, I'm going to go ahead and send you one more signal so that you can die as well. And then both children will end up dying. And we can put this in an else if you like that better. It's not needed.
I have a question.
Yeah, go ahead.
What's the difference between exit and return?
Return will make this function end, which then will take us back to our infinite loop. Whereas exit kills the process.
Okay.
Yeah, so exit is effectively the way we're breaking out of that infinite loop. We're done with this entire process and we're just going to die off. And maybe the more generic way of answering that is the return keyword makes a function immediately end. So when the main function immediately ends, the process is over anyways. When handle signal ends, it returns control back to main. If that makes some sense. So return always makes the function it's in immediately come to a conclusion. In this case, we don't want to just send control back to main. We actually want this process to die. All right, so let's see how we did here. So first process is going to tell the second process to start counting. They're going to send the kill command. The second process is going to go ahead and count. Count is currently for them is 0. So they're going to print out count is 0. They're going to kick it up to 2 for to 2 for them the next time around. Then they're going to send the message to their brother. Now that brother has actually offset their count by 1. Before they sent that original kill command, they said, oh, okay, my first number I'm going to count is actually by 1. So I'm just going to, offset my counter by 1, tell my brother to start counting. Then once the second brother tells the first brother to go ahead and count, first brother will come in and say, is 1 greater than 10? It's not. So I'll print out a 1. 1 will become a 3. Tell my brother. Brother comes back in. They say they're currently sitting at a 2. Is 2 greater than 10? No. Print out a 2. 2 becomes 4. Call my brother. Print out a 3. 3 becomes 5. Call my brother. Print out a 4. 4 becomes 6. Call my brother. Print out a 5. 5 becomes 7. Call my brother. Print out a 6. 6 becomes 8. Call my brother. Print out a 7. 7 becomes 9. Call my brother. Print out a 8. 8 becomes 10. Call my brother. Print out a 9. 9 becomes an 11. Call my brothers. Now we're getting towards the end of it. So 9 becomes an 11 for that guy. Call my brother. Brother says, okay, is count greater than 10? It's not. It's currently equal to 10. So I'll print out my 10. 10 will become a 12. Call my brother. My brother will see, well, my count's 11. Is 11 greater than 10? It is. Send one more signal to my brother before I die, then die. The brother gets that last signal and says, my count is 12. Is that greater than 10? It is. He'll try to send a signal to his brother. It actually won't go through because that brother's already dead. Okay, so that last kill command will be somewhat of a waste of time. And then he'll go ahead and die off. So we should have 6, 5, 6, 5, 6, 5, 6, 5, 6, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think that successfully solves the homework. Does that look right? All right, so questions about that?
Would it be easier, maybe not easier, but does it make more sense to just put count in shared memory? I thought that's what you wanted us to do. I don't know if it's, I don't know how much that changes.
Yeah, and we're going to do it. I mentioned that a few minutes ago that we could do that rather, because right now we're kind of playing a game with our own local copies of count, right?
Yeah.
And since both children know the job they're trying to do, they're kind of keeping track of their own count and then incrementing by 2 each time, and they're just kind of making it work. So what you're suggesting, and I'm going to do that version of it next, is let's create a separate place in shared memory. Now we could use the same place in shared memory that we use to share our process IDs, because once we have the process IDs, now we have that safe place in shared memory we can use. We could also create a new segment ID that we can use a separate place in shared memory for the counting, but we can use the original. All right, so both of these children have access to that segment ID, but what I'm going to do is I'm going to create the variable for my shared memory pointer up here. And then I'm going to set it in both children. Okay, that way both children have access to their shared memory variable inside of this handler. Okay, so then inside of here, after the second child gets, well, let's follow this. The second child will get the first child's process ID, prove that they got it. Then they'll put their process ID in there. And then jump into an infinite loop. We're not going to detach from the shared memory this time, because we're going to still be using that shared memory. The first child, after sleeping for a couple of seconds, grabs their brother's process ID from shared memory, spits it out. We're no longer going to need to manipulate count. We're no longer going to need to have a global variable for count, because we're going to use our shared memory for the counting. We're not going to detach from shared memory. Now, before this first child gets the ball rolling, he's going to go ahead and say star shared memory is equal to 0. Right, so he's going to start the initial count off at 0, then tell his brother to take over. So his brother is going to come in here. Oh, sorry. And say, is the current value of shared memory greater than 10? If it is, don't do any counting, but go ahead and send the message to my brother and die. Else, let's print out the current count, which is star shared memory. And we'll stay star shared memory plus plus. So we're not going to play the game of jumping by 2, because the two children are literally sharing the same place in memory for counting, but they are just going back and forth between each other for who's going to print out the next value. And then they'll call the other child. Right before this guy dies, he'll go ahead and detach from his shared memory. Again, good programming practice. The other child will do the same thing. So after they've tried to let their brother know that, okay, it's your turn as I'm kicking the bucket, they'll detach. Oh, did I not increment? We are going back and forth. Can we not use plus plus? I think we could have used, well, it's actually strange. Could we put it in parentheses and made plus plus work? Well, maybe not. Just because the nature of we are saying resolve to the value of a memory address, the plus plus operator would then be operating on the address of shared memory, doing math with the memory address. No, because I'm saying star shared memory. I really wonder what plus plus does. Do something here real quick. Printf %p. Actually, we'll say %D, %D, star, shared mem, star, shared mem. The first one should give you the value of shared memory and then add 1 to it afterwards. Second one should say the new one. We clearly saw that it wasn't actually incrementing the value. So we should see a bunch of zeros well, they should be the same value next to each other, not a bunch of zeros, because we are accurately updating here. So let's see what it does to the memory addresses themselves. It's not going to change the memory address. Yeah, the memory address doesn't actually tell us anything. This number tells us something. So what happens here is the way variables resolve. Here, let me put parentheses around it first. Pretty sure this is going to give me the same output. Yeah, it does. So it's interesting how C resolves the pointers. So this is how variables get resolved. If I was dealing with a normal integer, the plus plus operator knows how to work on a variable of type int. So it would effectively set the place where that variable is equal to 1 more than it currently is. In this case, star shared memory boils down to a number, not a variable. So since it boils down to a number, let's say it's 5. When I say 5 plus plus, sure, the 5 does become a 6, but it's not getting stored back anywhere because that is at that point the literal 5. So we can't actually increment a value at a pointer using plus plus. We have to do it this way. We probably can do plus equals 1. That should work. Yeah. Just kind of an interesting trivia thing that the plus plus operator is not going to function on the resolved value at a memory address. All right, so that should be a solution using shared memory. And we are going back and forth, right? 2, 1, 2, 1, 2, 1. Yep. All right, questions about that? Okay. Anybody else do it in any other interesting way? I think those should have been the most straightforward. Okie dokie. So with that in mind, here, I'll go ahead and save that. Share the code. All right, so if we look at this code here, we say, okay, well, where are their weaknesses? So we're certainly doing communication between 2 child processes. We played the game with the shared memory, letting them each know about their process ID so that we can raise flags on either one. And that seemed to be something that was easy enough to do once we had those process IDs. But if we're looking at weaknesses here, where do we still have an issue? We still have an issue here where we're sleeping, right? You know, where we're having you know, we're kind of having to time that initial interaction. Now, while this wasn't that big of a deal and we were only doing it one time, we can certainly have slowed down the sleep. We sort of had to, what we're doing right now is if we have 2 children kind of running around the park, and they're going to share a piece of information with each other. We're telling one of the kids to, wait a couple of minutes before he goes and checks under the rock, because the other child hasn't quite left his message yet, something like that. Rather than both kids might run towards the rock trying to grab their message. So the job of a child would be grab my message, then put my process ID in there. All right, so that's what each child would do, is grab the piece of information and put their process ID in there. So we need to somehow come up with a way of synchronizing those two children in such a way that we're not kind of timing it. So we have something called the critical section. So the critical section is a chunk of code that needs to be protected against anyone else executing it at the same time. A lot of times it's called mutex, mutual exclusion. All right, so we kind of need a way of protecting that code where we read in the process ID, store that process ID, write out our process ID, that initial negotiation of how the two children are going to get the ball rolling. Okay, so the way mutual exclusion is handled inside of, well, we have a couple different ways, but a popular way of handling mutual exclusion is through something called a semaphore. And there's two kinds of semaphores. We have binary and we have counting. So binary is always a 0 or 1. Counting counts down from a number, and as long as it is greater than 0, the resource is available. So with the binary one, we're going to say if it's 1, the resource is available. All right, so if we're kind of giving a real life example of how these semaphores might work, imagine we just had that example of we're gonna hide process ID under a rock, and both kids start darting towards the rock. Now, one of them, so in this case, that rock is our critical section. All right, because we only want one kid looking under the rock at a time. So whoever gets there first, they kind of trapped that area. They're in the critical section. They're the only one allowed. They have mutually exclusive access to that critical section. And then they can look under the rock, do their thing, whatever they're going to do, whatever logic they're supposed to do with that rock. If, they're putting their process ID in there after they read in the process ID of the brother, that's fine. And only when they're done doing their thing do they relinquish that resource? Do they relinquish the rock? So as they leave their critical section, they then give back access to that resource. So the binary semaphore allows 2, well, actually, we could say 2. It allows one process at a time to access a resource. And I could say process or thread. We're still working with processes here. Okay, but it allows one process at a time to use a resource that is protected by that semaphore. So you can think of the semaphore as kind of like a bouncer. Whereas the counting semaphore, this guy allows us to say, you know what, we have multiple resources, but not an infinite number of resources. So for instance, you go into a McDonald's and there's 4 cash registers at McDonald's. And, if 3 of the registers are busy, one's still available. So you would run up to the one that's available and you would grab that resource. You would start using that resource. So the semaphore would start off at 4. There's 4 registers. First person comes in, starts using a register, it drops to 3, then to 2, then to 1. Not until somebody comes in and checks the semaphore for, is there any available resources, and sees that it's a 0, do they then have to wait in line? And then then you have the next logic of which is the shortest line or whatever. All right, but semaphores give us controlled access to a resource, and typically they're controlling a section of code called the critical section, where we only want a limited number of users in that section at once. In this case, when we're trying to have that single thing, we're going to be using a binary semaphore to accomplish this. Oh, I did. Thank you. How far back do we go? Yeah. No real damage done. Just jump back over here to this guy. I'll just replace that with that. And let me delete those from the other one. Okay, there we go. Thanks for letting me know that. That was adding to the 250 class instead of the 450 class. All right, so let's go and let's look at semaphores. All right, so we have a name for a semaphore. So we'll go ahead and we're going to test this in some different part of our project. We're going to do ours with processes, so I don't need threads. So I'm going to go ahead and create a new project. I'll save this. Call this guy semaphore test. Put a couple of includes up there. We'll call the semaphore my bouncer. Okay. All right, so now what we're going to do is we actually are going to go a little bit different route with this. We do need to have the children go ahead and access the semaphores independently, because you see here that we open a semaphore. I'll go ahead and put that code in here. So we use a semaphore's name. So in this case, I'm calling it my bouncer. To open a semaphore, we create it if needed. I think if it's already created, then it just won't, it'll just open it. So we don't need to worry about having create for some and not creating for others. So we'll go ahead and open the semaphore. But what we want to do is we want to do this for the two children to open the semaphore. So we're going to say int PID is equal to fork. And we'll actually just do it between a parent and a child initially. So we'll say if PID is equal to 0, then we'll go ahead and open the semaphore. Else, we will also open the semaphore. So both the parent and the child here have, I don't know, you can think of it as walked up to the bouncer. When we say sem open, they've walked up to that bouncer. And then we have a blocking code. All right, so we'll just do a little print statement here. Printf, I am the child about to approach the bouncer. And then they're going to go up and sem wait for that sem ID. This is them trying to grab that resource. All right, so once they get past this line, so this line blocks until that resource is available. Then they get into the critical section. They do their thing. And when they're done doing their thing, they then leave the critical section, making it available to someone else. This off to the parent. Parent in the critical section. Now, in this case, since we're only having them do one thing, we can go ahead and unlink from the semaphore. So that's kind of like detaching from shared memory. All right, so both the parent, or both the child here and the parent are both competing for this single resource. This is what the child does in their critical section. This is what the parent does in their critical section. But because they're guarded by this semaphore, we're guaranteed not to have them both in that critical section at the same time. We're not having to do any sleeping. Now, the hope would be here that if I run this a bunch of times, sometimes it'll be the child, sometimes it'll be the parent that gets there. But depending on how fork works, it might just always be one or the other. Oh, I need to, fork is in. Either one is getting into the. Let me try not unlinking. Could also be with that O create thing. So O create is in. this guy. They're both stuck at the bouncer. I don't think we do it inside of a wait, or inside of a loop rather. Oh, some post. Sorry. Post is how we increment the variable. So we actually can control this. I'm going to just get rid of the sum weight real quick. I want to see who gets to this critical section first, if it's consistent. We need to have the parent. Gotta bring in sys weight. All right, so parent wins, parent wins, parent wins, parent wins, parent wins. All right, we're gonna say we tested that exhaustively and the parent always wins. So let's go that route. All right. So in this case, we're gonna kind of control it rather than create a race condition. We're gonna have the child go and do something. So the child is going to post. You can think of semaphores as special purpose integers. I'm going to go back here. Semaphore is a special purpose integer that increments and decrements atomically. That is, as if it happens in one CPU cycle. This avoids race conditions where two separate things try to increment the semaphore at the same time. It can't actually happen because of the way the semaphores are, how they're designed. If both of those kids in our example are running to the rock in the park, they both can't get there at the exact same time and actually both gain access to the resource. One of them will win, even if, you know, it's a photo finish, if you will. So this will have the child increment that semaphore, grabbing the critical section, and then closing the semaphore, and then we can go ahead and unlink. Whereas the parent will wait for the child to finish before they get into their critical section and do their thing. So with that in mind, we actually don't need the wait and all here. And we'll go ahead and still unlink. So parent and child, they both are about to approach the bouncer. Now we saw before that the parent definitely got to the bouncer before the child did, because they said they were in the critical section first every single time. But we see here that because we're using the semaphore, the child actually gets to the critical section first, whereas the parent had to wait for the child to finish before they got their job done. All right, so they were able to synchronize with each other to accomplish that task, to make sure that the child did something first, then the parent went and did something. Okay. So homework, given the semaphore example, and I'll go ahead and grab this guy. Best homework solution, this guy. Update the homework to use semaphores to share the process. Actually, let's just use semaphores to do the counting rather than signals. Submit link to the code and the self-assessment. All right, makes sense what I'm asking you to do. So we're going to use semaphores to synchronize the communication between the children. Okay, questions, comments, concerns, bribes? I will see everybody on Thursday.